I'm delighted to be able to introduce our next speaker, Dr. Yingying Chen. She's a professor of electrical and computer engineering and the graduate program director of information and data engineering and networked information systems at Stevens Institute of Technology in Hoboken, New Jersey. Dr. Chen is a professor in the Department of Electrical and Computer Engineering, and her research interests include cybersecurity and privacy, the Internet of Things, smart healthcare, and mobile computing and sensing. She's published over 100 journals and refereed conference papers in these areas. She received her PhD degree in computer science from Rutgers University, and prior to joining Stevens, she was with Alcatel-Lucent of Murray Hill, New Jersey. She's the recipient of the NSF Career Award and the Google Faculty Research Award, and she has also received the New Jersey Inventors Hall of Fame Innovator Award. Once again, I would encourage you to read her entire biography in your program today and read more on her professional accomplishments and her very impressive resume. But without further ado, I would love to introduce Dr. Chen and to allow you to hear from her on the topic of friend or foe, your wearable devices reveal your personal PIN. Dr. Chen.
Well, thanks a lot for the introduction, and I'm really happy here to give the talk and to share my research experiences and also our ideas in this area. And I think I understand that the cybersecurity area, and especially they have a very fast-growing trend in the Internet of Things. So I really like the symposium that the FDU have here. I think it's a great opportunity for both the researchers and also the students in this area to learn more, and also we can share the ideas and exchange the opinions in this area. I'm currently the Director of Data Analysis and Information Security Lab at Stevens Institute of Technology. And I'm also the Graduate Director of Information and Data Engineering program at Stevens. So first, I'd like to talk about some of the research that we're doing in the Data Analysis and Information Security Lab. So there are three main research themes that we're working on. The first one is cybersecurity and privacy. Okay, moving along in the traditional wireless security area, that we're looking to the identity-based attacks, anti-jamming, and also intrusion detection. And then recently, okay, we move more in looking to the smartphone user privacy and also the unobtrusive user authentication area. And I'd like to introduce a couple of projects that we're currently working in this area, so that to give you a brief idea. And furthermore, okay, we're looking to the smart healthcare domain and moving into the Internet of Things. So for the Internet of Things, we more look at for the end user devices, how they can help us to connect everything together. And we also work on the connected vehicles area. That is, we're looking to how to reduce the driver distraction problem by checking whether the driver is using the phone while or texting while they are driving. Okay, so let's look at how we are doing this driver phone detection problem. Okay, when we try to reduce the driver distraction. So we understand that the driver distraction problem getting more and more severe, especially when the driver is taking a phone call or texting while they are driving. So this becomes a life-threatening problem, and it's also threatens not just the driver itself, but also the other vehicles in the road. So what we do in this area is that we're looking to how can we detect whether the driver phone is being used while the vehicle is moving. While if the passenger's phone are being used, then we let the passenger to continue to use the phone while the vehicle is moving. So we have two approaches in this work. Okay, one is that when there's incoming call to the phone inside of a moving vehicle, what we do is that there's an app that we install on the phone, so the phone will automatically emit a customized sound, and this sound is unobtrusive to the users, or we say that to the occupants on the vehicle. And then this sound will be automatically played back by the vehicle's audio system, and the phone will record the sound and then perform acoustic ranging, so that the phone can automatically determine whether it is on the driver's side or on the passenger side. So this is how we track whether the phone is on the driver's side or on the passenger side. And in our once we publish this work, it actually attracts many media outlets report, including the Wall Street Journal, MIT Technology Review, and many other media reports. So moving along this direction, so we have a second work that is not just relying on the Bluetooth systems on the vehicle. What we do is that we find that when the vehicle makes a turn, the centripetal acceleration will be different if the phone is on the driver's side or on the passenger side. So by looking into this simple physics phenomenon, it also helps us to determine whether the phone is on the driver's side or passenger side. So this is a fundamental finding, okay, to help us to track, okay, if the phone is being used by the driver or not. Once you find this, there are many upper-level applications could be built upon it. Okay, we can either, okay, let the driver defers to take the phone call if the phone call is not coming from the critical list that the driver listed, like from his spouses or from the driver's family members. So we can defer the phone calls, or we can defer the text message notification until the vehicle stops at a stop sign. So a lot of things you can do once you know this fundamental information, whether the phone is on the driver's side or not. And once we look into the smartphones, right, we know that there are many sensors on it. So this is a project that is very related to the Internet of Things, is that we find that you can utilize the sensors on the smartphones to help you to perform the user verification, or we say the user authentication. Okay, especially all the smartphones these days, they're equipped with accelerometers and gyroscopes, right? So by looking at the accelerometers, it tracks, usually we use that to track the people's steps every day, and also measure the activeness of the user. But by also take a closer look of the accelerometer, what we can do is that we can extract the gait patterns from each user. And the gait pattern recognition by using the accelerometer, it's a traditional approach. However, in the previous research, people always using the high-grade accelerometers, which has a very high sampling rate in order to determine the user's gait patterns. And the challenge here is that these days when we have smartphones, it only has a low-grade accelerometer. However, if we look into this low-grade accelerometer, we also can determine the gait patterns, okay? And by looking into the gait patterns, it will help us, okay, to find the uniqueness of each person. Okay, the thing is that for each person, your gait pattern is different. So by examining the gait patterns, we can determine, okay, whether this is the original user who's working with this phone, or, okay, the phone has already been stolen, okay, by some attackers or by some adversaries. And what the smartphone can do for us more, okay? Besides that, you can use it, okay, to perform the gait pattern based user verification. What you can also do is that we look at the touch screens, okay? The touch screens provide rich information that you can extract from it. So that triggers our idea is that whether we can perform the signature verification, okay, by using the enhanced information from touchscreen. Okay, traditionally, when you perform the signature verification, what we do, you match the segments inside of the signatures, right? So that you match that and then find if there's any forgery going on. And when you sign on the touch screens or when you sign on any of the touch pads that you have these days in the grocery stores. So what we can catch from the touch screen is that we can catch your signing speed, okay, your signing critical segments that we can extract it, and also the pressure, the touch pressure you have. So with the combination of this information, actually each person you have a unique combination. It's very hard. It's very hard for attacker to get all the information from you, okay, in all the different aspects. Even if attacker, they can perform this shoulder surfing, they can get, okay, your signature when they observe when you sign. However, it's very hard, okay, it's very hard for the attacker to mimic the same kind of touch pressure, the same kind of signing velocity that you preserve in your own genuine signature. So that is what the touch screen can do for us to enhance the e-signature verification to secure all this booming security, to secure all this booming mobile transactions in these days. Okay, and then another direction I'd like you to take a quick look is that by looking to the wireless networks, the Wi-Fi networks these days, okay, the Wi-Fi networks help us to get online, okay, especially okay, when you're at any places. It's very easy for us to communicate with people and then to send out files. The thing is that what we can do more with Wi-Fi, okay, we find that we can use the Wi-Fi signals to help us to track the vital signs. Okay? And these days, okay, we have these fitness bands, okay, to help us to measure the step counts. Okay, usually we do the fitness bits, the Fitbits, and also the Jawbone, all these fitness trackers. Okay, however, okay, it can only do up to the point that they can measure the heart rate, but they cannot capture your breathing rate while you're asleep. Okay, but many people, they have sleep irregularity at night. Okay, especially for those people, they suffer from sleep apnea. How you can do the early diagnosis of it? Okay, it's a very challenging problem. The existing solution is that you let the patient go into the clinical offices. Okay, they stay there for 2 days, for 2 nights, and then they have all kinds of sensors installed in their body and in their head. Okay. The problem is that the people's regular sleep patterns got disturbed, and it's very hard to capture their sleep irregularity just for 2 nights. Okay, and the patients, they need to suffer from multiple sensors, okay, wearing them during their sleep. So now our idea we want to do is that a way, okay, to let everybody, you can track your sleep at night without wearing anything. Okay, so in that sense, okay, you can capture the early sign of sleep irregularity at home by just measuring the breathing rate at home. So the idea is that we try to use the existing Wi-Fi systems that are already installed at home. Okay, this kind of solution, okay, is low cost and also very easy to deploy, and it is scalable to thousands of homes. So we look into the fine-grained channel state information, and it can help us to detect the minute body movement at night. Okay. So we look into both time domain and frequency domain, and it can help us to measure the breathing sound at night. And we see that this is a very significant finding, and it can be a great add-on, okay, to the sleep monitoring at home. In addition, okay, to the regular sleep monitoring activities, such as your turning over, your snoring, and your coughing at night, okay, by using the regular Fitbit bands and also other smartwatch wearable systems. Okay. And we also look into the work that is, we look into the part is, we look at the privacy leakage on your smartphones. Okay, these days you have so many smartphone apps being installed. Okay, we like to see that by just examining these apps, okay, for each app when you install, you agree the terms and conditions. Okay, some of them, they're going to use your locations, and some of them may access your camera. Okay, you will allow them to do that, right? Because I want to use that app. However, you do not know, okay, what kind of information could be leaked from it. And especially, okay, when this kind of information could be gathered, okay, by the advertisers, okay, and across the users, okay, what they can do with such information. Okay, so we look into the work in this area, okay, is that we find that, okay, by just grouping this information from multiple users, okay, the advertisers or the third-party server, what they can do is that they can infer the user's social relationships, okay, without looking to the user's Facebook, the public social media, by just examining the private information that is being leaked in your app. They can derive their social relationships. Those are the physical social relationships, that is who are your family members. And also further, okay, we find that we can this kind of privacy leakage, they can infer people's demographic information, okay, without you attending a survey, okay, saying that how old you are, what kind of job you're doing, what kind of income you earn each year. By just looking into the privacy leakage information, you'll be able to derive people's demographic information. So that is actually set up a warning flag, okay, to the users, because for the second part we haven't published yet. We're going to publish later this year. Okay, we want to show that the third-party advertisers, when collecting by just using your apps normally, okay, they cannot just derive your social relationship information, including your family relationship, your colleague relationship, but they can also derive your demographic information. Okay, this is all being done in a systematic way. Okay, so let me, I think I just skipped this part. This is another type of work we want to do in the cybersecurity area. That is, we are looking to the visible light communication. Okay, so the visible light communication is that you embed the secret signals, secret signals when you're playing video, and then you can use your smartphone's camera just to capture it, and then decode the secret information from it. So it also becomes a very interesting area. People are looking into it, okay, by using the screen camera channel, that you can play the normal information without the user's notice, but you can also embed the secret information inside of it by using the visible light communication. Okay, so now I'll go back to what I want to talk about today. Okay, before I talk about we're using wearables to see that how it can reveal your personal PIN number, I like to see that, okay, this is the originating for our work. Okay, I think 2 years ago, okay, we started the topic, is that we find that, okay, if you put a smartphone, okay, beside your keyboard, okay, or you beside anybody else's keyboard when they're typing, okay, these days your smartphone usually equipped with more than one microphone, right? Typically 2 microphones. And those microphones can pick up the typing sound. Okay? By picking up those typing sound, that when you put the phone beside your keyboard, okay, what we can do, the smartphone with the 2 mics, okay, we can do the time difference of arrival. Okay, so this is what we call acoustic ranging. And acoustic ranging can provide us with centimeter level accuracy. Okay, so when you do this, okay, it will help us. It can help us to snoop what other people are typing. Okay, so on one side, we can utilize a dictionary, where we see the contextual information to help us to infer, okay, what people are typing, okay, when they're sending emails. Okay, those need the contextual information. And also, by adding on to this, using the fine-grained MFCC features, on top of the time difference of arrival, it can just help us to localize the keys in an accurate way. By doing that, it can help us to infer the password. Because password is random, we cannot looking for the contextual information or the dictionary to infer it, right? But you can see that, okay, by just using a single phone, okay, we put it beside a keyboard, okay, you'll be able to snoop the keystrokes, okay, and then to achieve the millimeter level audio ranging by using both time difference of arrival and also the fine-grained MFCC features to do that. Okay, so this is using acoustic signals to help us. You have the typing sound, right? So you can see that when you're typing in the public, okay, or typing in a library, okay, in any places, if there's a phone placed beside it, not your phone, somebody else's phone, okay, your keystrokes could be snooped. Okay? And meanwhile, okay, the attacker, if they really target to you, what they can do is that they can implant a malware inside of your phone. Okay, so even if you put your own phone beside your keyboard, okay, your phone, the malware inside your phone, they're going to send out the recorded typing sound, okay, to a remote server. Okay, then what you typed on the keyboard, okay, will be leaked out. Okay, so by looking into this, so this is now our origination of the work is that, okay, we see that, okay, these days actually when you're typing in the public, okay, a lot of things could be leaked. Okay, then this leads to now work is that, okay, we're looking into, okay, when you wear your wearable devices everywhere, right? These days you usually wear a Fitbit or a Jabon. I usually wear a Jabon every day, or you wear a smartwatch. Okay, what is the security vulnerability behind it? Okay, so this is now work about we're looking into how the wearable devices can reveal the personal PIN number. So this work has received the Best Paper Award in the Asia CCS this year, and it also been reported by a CNN, IEEE Spectrum, Fortune, and over 60 media outlets. And this is a joint work with my students, Chen Wang, Xiaonan Guo Bolu, and also Yan Wang, and also he was also my student when he was working on this project, and now he graduated and joined Binghamton University as associate professor. Okay, so we've already understand the motivation, okay, of wearing the fitness trackers, right? So these days I've already talked about a lot of applications that we can use besides the original usage that are present by this fitness trackers and smartwatches, right? So we wear it almost any time that we want because it can help us to measure the steps especially, and also perform the heart rate measurement and also sleep monitoring at night. And however, okay, if we want to look into this, okay, because we wear it any time, okay, 24 hours a day, so we wear it to do any tasks that we want. Okay. So is it possible, okay, now sensitive information could be leaked? Okay, so in this work, okay, we're looking to one aspect of it. Okay, why is that? Okay, because the thing is that usually, okay, one of kind of sensitive information is my personal PIN number, right? My personal PIN number is something that I need to use my finger to input. Okay, it could be the ATM PIN number, it could be the electronic door lock, okay, that try to enter into this key-based security system, and also I can type on the keypad, okay, in order to enter a server. And I want to say that, okay, there are a lot of work, okay, we are looking to. We have been looking into this, okay, what kind of attackers have already do before. Okay, previously, when attackers, they try to find out your ATM PIN number, okay, what they do, okay. First of all, they can do the shoulder surfing. They get very close to you, okay, but these days it's actually, usually you'll notice that they'll get exposed easily. And then they can install the hidden camera, and also they can perform the keyboard overlay. Okay, all of this, I think these days, all the security in the banks, they have already discovered all these problems. Okay, so they put enhanced security in the banks. So the hidden camera and also a keypad overlay, okay, probably still happened in the developing countries, but in US, okay, it has been largely reduced these days already. Okay. And for the other works that we talked about, okay, is the one that we talk about. I just showed you the example to snooping the keystrokes, right? And for that one, okay, we usually rely on the audio-based system, okay, such as your phone. We use the microphone to record the sound, or people can also use the vibration-based attacks, that we can put a vibrator that is closer to a keyboard. We can also pick up the sound. Okay, we call that as the vibration-based attacks. Okay, while in this work, okay, what we want to show you, is that if we do not rely on any additional hardware, you will see that, okay, whether your wearable device is safe or not. Okay. So the basic idea we want to explore here is that we look into the embedded sensors in wearable devices. Okay. In the wearable devices, they equipped very similar sensors that as you have in the smartphones. Okay. The only difference is that they're integrated. They have less number of sensors and they use integrated sensors. Okay. So for these integrated sensors, what they can do on your wearable device, okay, if they can capture, okay, your finger movement, if they can derive the trajectory of your finger movement, then we'll be able to find out what you're doing. Okay, and especially for this fine-grained finger movement, okay, you can see that when you touch the keys, the pins, okay, what you do is that your finger will accelerate first and then decelerate, then stop on key 1, and then, okay, you move to a key 2, okay, with acceleration and deceleration again, right? So this kind of pattern, okay, could be captured by the accelerometers in your wearable devices. Okay, and if this information is being captured, and if we can recover the trajectory of users' finger movement, you'll be able to find out what is the pressing point and what is the releasing point. By looking at that, further you'll be able to determine, okay, what are the key clicks, right? So if we take a closer look of the embedded sensors on your smartwatch or wearable device, okay, they have an integrated sensor unit. Okay, it is for accelerometer, okay, which measures the 3 axes of acceleration in x and y, z direction, okay, in respective to the wearable device. And then the gyroscope, it measures the orientation in 3 axes, okay, along x, rotation, y, rotation, and z rotation. You call it pitch, roll, and yaw. And then the magnetometer. Magnetometer, okay, it helps actually to find out, okay, what is the Earth north. So this integrated sensor, okay, it's very small. Okay, it is very small, in your, being planted in your smartwatch, and also the fitness trackers. So this, the first two, especially the first 2 sensors, it contributes the measurement of your steps every day. Okay, so we rely on that to measure the steps. So then what we can do? Okay, let's look at what the attackers can make use of this sensor data. Okay, if the attackers, they can access this wearable sensor data, then they get a chance, right, to derive what is the clicks you make, okay, what is the finger movements you do. So there are 2 possibilities of attacks that we have investigated. Of course, there are also many more other possibilities. So first of all, you can have a malware that is implanted in a smartwatch. Okay? So we understand that your fitness trackers, they periodically sync with the user's smartphones to send the data over, right? So that we can look at the historic information, the statistic information. So the adversaries, they can implant a malware on smartwatch, okay, and then when you do the sync, the smartwatch will send the sensor data back to the adversary's phone, and meanwhile, they send it back to their own phone. On the other side, okay, without putting the malware on the smartwatches, the attacker, they can do is that they can install malware on the user's phone. So once the user's phone periodically synced with the wearable devices, the user's phone get this data. When they calculate the statistics, meanwhile, this data could be sent back to a remote server, being accessed by the attacker. Okay. It is also possible when we do the wireless sniffing. Okay. The wireless sniffing is that you have the user's wearable device and have the user's smartphones. So they are periodically synced to each other. Okay. So what the attacker can do is that they can sniff in the Bluetooth traffic between your wearables and your smartphones. Okay. And because of the low energy concerns, okay, we want to lower the energy consumption on your smartwatches and wearable devices. These days, they did not use the standard Bluetooth protocol. Currently, we all use we call the Bluetooth Low Energy Protocol, BLE protocol. And the BLE protocol, the thing is that the encryption process is very easy to be decrypted. Okay, the security level is much lower than the standard Bluetooth protocol. Okay, so there are already existing work showing that how to decrypt the BLE traffic. So the attacker, they can just perform the wireless sniffing and then get the embedded sensors data. Okay, so once they get the data, okay, what we want to show is that actually in this kind of approach, okay, it's going to be a training-free approach because the user, we do not want to cooperate. We do not want to leak any information to the adversaries, right? So the users are not cooperative, so it is training-free, not like a lot of work, okay? These days, what they do in the security area is that they require training. Okay, they require the user's cooperation. Okay, so in this approach, it's training-free, and also when you recover the PIN number, basically, there's no contextual information because the PIN number is random. And also, there's another thing usually you need to take into account. Okay, is that when the user, they wear the wearables, okay, there's a coordinate that is irrespective to the user's wearable device. That is what is integrated sensors collect the data for. That is the X and YZ. That's XYZ coordinate they defined. And this coordinate is different, right, from the keypad coordinate. Okay, so when we look into the sensor data, how can you derive the sensor data and match it to find the fine-grained finger movement on your pin pad? Okay. So this comes into play as we see that there's an integrated sensor, right? Besides accelerometer, gyroscope, there's a magnetometer. So when these three sensors integrate together, especially the magnetometer, it tells you what is the earth noise. Okay. So this provides a new information called quaternia. This is also a sensor reading that you can directly obtain from your smartwatch. Okay. So this quaternia basically can help us to derive the wearable device coordinate to the word coordinate. Okay? And once you convert to the word coordinate, then we can convert to the keypad coordinate. Okay, so basically I think when they construct this integrated sensor, they do not know that there is so much information that could be extracted out of it. So let me quickly go through our framework overview, what we have there. Okay, so we first of all, okay, we need to do the key click detection. Okay, and then you can perform the segmentation, right? The key click detection is the first step we want to know. You need to determine how many key clicks the user performs. Okay? And then based on the key clicks information, okay, we also need to do the data calibration. The data calibration involves noise reduction and also this quaternion-based coordinate alignment. Okay. Then we're going to perform this fine-grained subpath recovery. What is subpath? Subpath is that we see that the subpath is defined as the distance between two consecutive key clicks. Okay, so you need to determine what's the distance and also what's the direction. So there are two things you need to define the subpath. Okay, and once you get the subpath, we need to put them together. Put them together is that you're going to derive the ping sequence. Okay, and how do we put them together? Okay, so what we want to look at is that you remember that when you enter the ping number, usually the last key will be the enter key. So by looking at that, okay, we derive an algorithm called backward ping number sequence inference algorithm. Okay, so just to go over this fine-grained subpath recovery, okay, if we look at the input we have on a keypad, for this example is 5419, okay, and then the enter key. So this is we show the z-axis readings. So what we can do is that first of all we need to do the key click trace segmentation. Okay, once you do the key click trace segmentation, you'll be able to find out what are the estimated distance between each key clicks. Okay, and then for each subpath, we perform a subpath recovery based on both distance estimation and direction estimation. So for the distance estimation, okay, what we do is that you use the z-axis of the aligned coordinates, okay, for the accelerometer readings, and then you're going to turn into the x and y plane, okay, to find out the distance calculation. Because actually this is a very small distance. Okay, we call this as the fine-grained small finger movement. Okay, and I won't go through the detailed distance estimation we have. Basically, we need to find out the crossing points. Okay, we need to find out the unique patterns that are embedded, okay, in each finger movement in order to accurately determine the distance. Okay. And we also need to further, okay, perform the subpath direction derivation. Okay, that will also utilize both accelerometer readings and also gyroscope readings to help us to determine in which quadrant the direction could be, and then further to use the x and y offset to help us to find out the angle direction. And finally, okay, when we try to put the ping sequence together, okay, one thing we find is that, okay, if we just directly put the ping sequence together, what we have is that if we estimated one digit wrong, okay, the subsequent digits could all be wrong. And this will actually involve accumulated errors, okay, when we do this subpath integration. Okay, so what do we want to do? What we want to do is that we try to find all the possible candidate sequence. We're starting from the enter key, okay, and then by looking at the subpath, the distance, the first distance estimation between the enter key to the last digit you have, in this case is 846, right? and you try to find out all the candidate calculation. Okay. By looking to all the candidate calculation, then we try to match into the keypad layout. And by looking at that, it will help us to find the pin sequence with the minimum error, with the smallest offset. So bearing that in our mind, okay, we derive this tree-based key sequence inference. Okay, that is, you can see that you're starting from the root, the enter key, and then for each root, you actually have 10 children. Okay, and what you do is that you use the mapping method and the tree traversal method, okay, to find out the constructed minimum accumulated Euclidean distance, and that is the candidate, the top candidate for a pin sequence derivation. So now I want to take a few minutes talking about our experimental study. So what we have studied is that we tried 3 different kinds of keypads. One is the real ATM machine, and the second one is the detachable ATM pad. This is the detachable one, so it allows us to do extensive tests. While for the real ATM machine, we can only talk to a bank that is willing to do the experiments with us. So we go there from time to time. We cannot continuously let my students always entering the pin numbers over there. Okay, and we also tried this keyboard-based number pad, and that helped us to test the keypad-based security system. And we tried 3 different wearable devices. Okay, one is the LG smartwatch and the Moto 360 smartwatch, and also the IMU sensor. The IMU sensor represents our test for the fitness trackers because it contains the same integrated sensor as all kinds of fitness trackers. And we involved over 20 volunteers, and we tried the 4-digit pin sequence, and these days we also increased it to the 6-digit pin sequence. So we built an app, okay, that the app installed on both smartwatch and also in the smartphone. Okay, that help us to collect the data and also sync the data back to the smartphone. And this is our testing system, the GUI of our testing system, showing us what is the raw data, okay, what we collected, and at each step, what we do, we perform the feature extraction, and we perform the coordinate alignment, what the data look like. Okay, and also it shows us, okay, this is the simulated keypad, and it shows us what are the possible combinations of the keys. Okay, so these 2 figures just show you the performance of our backward pin sequence inference algorithm under these 3 different kinds of variables that we tested. So we show the successful rate and with the number of top candidates that we have. Okay, and usually we see that if the sampling rate is high in your wearable devices, so basically we find that you can, why we try these 2 different kind of smartwatches, okay? The LG W150 is a higher end smartwatch. It has a sampling rate of 200 Hz. Supposedly it's more accurate in capture your step measurements, okay, and activeness of your daily work. While the Moto 360, we can reduce it, it can have like 25 Hz sampling rate. So it's a lower end smartwatch. And you can see that actually the lower end smartwatch is safer, okay, because the sampling rate is lower, while you have a higher end smartwatch, the sampling rate is higher, and it has the higher possibility, okay, to reveal your personal information as well. Okay. Okay. So these are just some more information about the distance estimation that we do. Those are intermediate results that we want to show you is that how we perform the distance estimation in each subpath when we try the different length of between the subsequent keys. Because on the keypad, you can still derive the define the subsequent keys that is in either a very short distance and the medium distance or the longer distance, which is in the diagonal area that is across your keypad. Okay, so to conclude my work, okay, I hope you can get some sense is what the these days what Internet of Things can do for you, not just from this one work, but for the also other work that I introduced, right? You can do the sleep monitoring, you can do the driver phone detection, you can also do the gait pattern recognition. And on top of that, the security and privacy becomes a very important issue. So that's why I showed you the work that we use the smartphone, we can snoop your keystrokes, and also when you wear your wearable devices that can basically reveal your very private personal PIN numbers. Okay, so that concludes my work. Okay, thank you.